So how do we go to with the control laws? Well, we have our dynamical system, state, actuation. There's a fast loop. In an experiment, we may be able to respond in 1 millisecond. We measure something and we immediately actuate. And then in 5 seconds, typically in a wind tunnel, we can determine if the controller is good or not, if the drag is increased or decreased. So we have the cost and we feed it back to our machine learning box. We want to solve this regression problem. The method which we are using is genetic programming. Who of you has learned about genetic programming? Well, quite a bit. So I learned it in 2013, and it has changed my career. So what does this machine learning control or this genetic programming do? You start initially with a number of random control laws, and I'll show you something like a cartoon of this process. These are some minima, so this is our control landscape. And there are different types of minima. We start with something like, I think here we start with 50 control laws. And this is, in quotation marks, our first generation. And then there exist a couple of genetic operations which create a new army of soldiers somewhere else. So this is the second generation. I will elaborate this in my third talk. So this is second generation, and we see this point gets gradually discovered. You can guess what happens in the next one. This one he calls in all the other points. Now one gets dangerously close to the real minimum. Now it goes here. So we have this one populated, this one populated, this one populated. And so at the end, essentially most of the control laws are close to the real minimum, and we still keep exploring the whole control landscape for some other elements. So this is the idea of genetic programming. Why aren't we doing it? So this is a mixture between exploration and exploitation. Why aren't we doing a gradient search? Well, if you go with a gradient search in such a terrain, you end up in a suboptimal minimum, or it's rather likely to do so. So does it work? Well, we have applied it to the cylinder bag, more precisely to the fluidic pinball. So we are invited to visit Nang's and Guy's postdocs for this purpose. I will go now to a slightly more complex flow, namely the flow behind an Ahmed body. The flow comes from left to right. The Ahmed body is mounted on a drag balance, so we can measure the drag directly. We have 4 independent actuators here. We have something like 12 sensors here. So now the name of the game is determine these pressure sensors. Use these pressure sensors to determine an actuation which minimizes somewhat the drag. Could we apply the model-based approach? Well, let's look at a simulation. So in the simulation, we see here the p-value, so we can see a lot of different frequencies. A low frequency, Stroll number 0.2, a very low drift by stability, we see high frequencies and so on. So you would not expect that this would be easy to model with any method. In fact, nobody has done it until now. So now we run our magic box, which I will explain later on. And our ansatz is take the actuation as a function of our sensor signal, and we get something like drag reduction of 22% with an energy investment of 3%. So overall, it's positive. And it takes less than 1 hour testing times, 250 individuals. The controller which we get is all actuations are in unison, and the actuations only listen to a single sensor signal. So why this? Well, it only listens to this sensor signal because the best forcing is high frequency forcing. And this sensor is the only one where you can essentially sense the induced vortices actuated on the frame. So the other ones have a too large signal to noise ratio. So with this, we get these reductions. Note what MLC did. It has done 2 things. Number 1, 3 things. Actuator selection, sensor selection, and using the controller, all in one brush. And so if you use other techniques, you need to have a linearized dynamics so that you can apply any other techniques. What is the physics behind it? Well, we have the actuators here and here. The wake regions, here you see the U component, is approximately the same length, but we reorient the shear layer here. We vector it a bit inward with some co-under actuators. So we make the wake a bit more aerodynamic. And so we do aerodynamic bowtailing, and this gives us a drag reduction. Now, I've talked already about control landscapes. At some point, I will teach you what proximity maps are. Anybody knows who proximity map is? Okay, so I will teach you something new. This is good. So what we do here, we do a proximity map of the controller. And so all you need to know for the moment is that these points which you see here, so these dots here, are controllers. And we map them in such a way that if the controllers, if these points are close, the graphs of the controllers is similar. So if the points are far away, they have different controllers. Here you have similar controllers. And when we build the proximity map in an automated way, this is how it looks. We have a couple of minima here. We have a couple of maxima here. And essentially, as the grayer area correspond to drag increase, the whiter areas correspond to drag reduction. At the end, we end up in this corner. And this asks, of course, for an explanation. We would expect typically a minimum in the inside. It turns out that this gamma 1 here corresponds to the frequency. This is high frequency, this is low frequency. This gamma 1, gamma 2 happens to correlate with a duty cycle. This is low duty cycle, small duty cycle. This is high duty cycle. So the best thing is to have very high frequency with a very small duty cycle, but this turns out to be the limit of our actuator performance. So when we are doing the analysis, we see that our control effect is essentially the limiting effector of our control is our actuator performance. So these are the type of insights which you get with machine learning control. And I hope I've convinced you now about one thing, that really we are talking about a paradigm shift, which machine learning does for our for fluid mechanics, particularly for turbulence control. I would argue machine learning makes turbulence control student-proof. So you can bring them quickly up to speed, and they can do some amazing results in the experiment or simulation. So in the past, you had to fight Godzilla, so you had a complex flow, you had to understand it. From your understanding, you build your model, and after you have your model, you add your control, you do your control design, and after the control design, you simplify it a bit, and then you test and tune the control in the plant. So it needs lots of human modeling. You get, at the end, typically simple controllers for 1 or 2 frequency. So big effort for some simple dynamics. And so machine learning is a bit like the wish-fulfilling fairy. It does the opposite. So you take some program of somebody, let's call it genetic programming. You do the optimization in the plant. Suddenly, you figure out a good actuation mechanisms. And by the way, your understanding is very limited. So in most of the cases we are doing, the type of control which we get is different from what we have expected initially. We get different frequency and different modes. So essentially, understanding in the first approach is a limiting factor for the, at minimum, for the control design. So what machine learning does, it does a control optimization in the plant, and you have the optimal controller. Now you know the winner. You use this mechanism for the modeling something which really matters. So 20% drag reduction or 2% drag reduction. And from there on you go to the understanding. And this is the easy path. I mean, this is the expressway. And now you can get fully automated complex controllers within something like 1 hour of wind tunnel testing times, and I can show you wonderful results. I will show you wonderful results for distributed actuation for jet mixing. And you must admit that the right part is a bit more attractive than the left part. So I've worked now 30 years on the left paradigm, and there are few students I want to put through this. So none is very smart. He can do it and rewards us with a lot of insight. But normally the right side is easier. And by the way, machine learning does not only make turbulence control student-proof, it also makes modeling student-proof and analysis student-proof. So at the end, you can always have your programming package where people quickly get to some results. So we have started with machine learning. We have discussed control and modeling. I've shown you an example of model-based control. Think if you would apply it for 10 actuators, 10 sensors, and maybe a turbulent boundary layer. Machine learning control, and nobody prevents you to use machine learning not only to determine the control, but in principle, you can also use the machine learning to determine the model. If you are looking for a black box model, so this M over there, what do we want? We want a function which translates our inputs, our actuation commands to the same or similar sensor signals. So this is the idea of a black box model. So essentially, instead of having a function like the controller from the sensor signals to the actuation, we now have a function from the actuation to the sensor signal, kind of the inverse. And the cost function is to have a good match between the measured sensor signal and the modeled signal. Now you put the box here, and you get a black box model in an automated way, a non-linear one. Now you can do many other things. For instance, you can take the controller and directly model it, project it on the cost. Does anybody know how to do it? Well, it's difficult if you have a couple of data. This interpolation is possible, shown in the sensor. You may want to use your sensor signal to estimate your cost. For instance, you have the pressure signals and you would like to know the drag. And there are many estimators which you can be possibly interested in. And what is now very, what we have almost reached is we can build near-optimal control models and estimators with much less testing time. Maybe 15 minutes wind tunnel testing time, not in thousands of runs, but in something like 100 runs. And so a lot of these tasks can be automated with machine learning. And this is our future. And with that, I want to conclude, and I'm open for more questions. May I make a photo of you? Yes?
Did you try the von Karman weight with the machine learning control?
The answer is I would have liked. We did it for a slightly different configuration, a fluidic pinball. So 3 cylinders with 3 cylinders rotating. But I'm pretty sure I know what would be the outcome. The outcome will be phasor control. So in all will be phasor control. If you look at the dynamical system, describing the von Karman vortex shedding, then the machine learning control gives you phasor control. I think we would get the same thing also in the original plant. I would have liked to do it, but our resources are limited. Good question. Thanks.
I have a quick question. At the beginning of your lecture, you said that if you have to control something that is more than 10-dimensional or something, then control becomes problematic.
Yes.
Is it there any similar rule of thumb in terms of cost of your cost function evaluation?
I like it. So, very good point. So the question is, what is the scaling? So what happens if you go from maybe 0 to 10 inputs to 10 outputs? And so typically this is a range where we did machine learning control. And it turns out that you can increase your sensor signals. You can go from 1 to 20, probably 100 and sensor signals, and your learning speed will be approximately the same. So because at some point machine learning listens to the sensor, there's some redundancy, this works. But if the actuation is not strongly correlated, if you do different actuations at different points, if you have to use different frequencies and so on, then the learning time increases. And so my rough estimate is the learning time is proportional to the logarithm of the number of actuators, assuming that the actuators do something different, which is a small increase. But we did not go to, one of our next goals is to go to something like 100 actuators. So Lucata Festa has a beautiful plant for this. And we also have a similar plant in high lift configuration in TU Braunschweig. So then we will probably push the methods to our limit. So are you asking if we can do actuator design?
Yes, finally, if you have a model and you see there's a limitation of an actuator you're using.
Yeah. Okay. Yes.
Then what's the extent? What should the actuator do? What would be better?
Oh, a good question. The answer is yes. There's a possibility. And I will be a bit technical. So if let's say if you have something like a three-dimensional parameter space and you figure out that this is your ridge line here. So essentially on this line, essentially you have a local minimum here, but you have a change here. So if you continue the ridge line, then you can essentially predict changes which you did not have in your original data. So we're doing this with Wolfgang Schröder for the turbulent boundary layer, but we can also extend the ridge line to controllers. So this is a new concept. And the interesting thing about the ridge line tells you if you have an easy play or if you're hard play. So if you do the ridge line and figure out you always go inside your data domain, then you are screwed. You can only improve things by an order epsilon. But if you go to the fringe of your domain, like we have seen here, then you know what you need to do. So in case of the actuator, increase the frequency and decrease the duty cycle. So the machining tools give you hints. The next thing what you would like to do, you would like to have a tool which determines the ideal actuator. If you should blow, or if you should suck, or if you should have zero net mass flux, and so on. And this will take a long time. The problem with machine learning for these things is that machine learning is based on the idea that you have something like rich data. Machine learning cannot do extrapolation, it can only do interpolation. So you need to have a lot of data, essentially, to use these data-driven tools to figure out what type of actuator you can use. So this will be one of the problems which will probably accompany us until our retirement. And I hope that maybe one of the students will solve it, because it's very hard and requires one person who dedicates probably 5 or 10 years of his career on this problem. Very nice. So you need something like a metric. So if you have two velocity fields, you have to determine how close they are. What do you take? Typically, you take something like the Hilbert space norm. So this is one thing. And in the locally linear embedding, there's also a parameter. For instance, if you have if your neighborhood is too small, essentially, if you have 2 points, but you have a 3-dimensional neighborhood, forget it. So you need to have a lot of data points in your neighborhood in order to essentially resolve or approximate the manifold. So there's a minimum threshold for number of neighbors. And there's also a maximum number of neighbors. If the area is too large, where essentially the manifold cannot be linearized anymore, then it's also bad. So somehow you have to determine the sweet spot, and this is the design parameter. So typically there's a number of nearest neighbors which you have to design. And from there on, the things are pretty automatic.
So the approximation is locally linear.
Yes.
Why are we constraining, like, is there a particular reason for constraining the weights to be non-negative?
I see, I mean, at some point you need to have something like a positive semi-definite weight matrix and these type of things. And I suggest you ask, I will answer the question in my second lecture. Thanks.
Have you ever tried to use machine learning to build some kind of adjoint mode for control?
The short answer is no. Are you satisfied with this, or do you want to know why? So, well, talking about adjoints, you need to have something like a backward propagator, right? So you have a forward propagation in time, and with adjoints, you need something like a backward propagation in time. And so, in principle, if you have these tools, probably machine learning will also help you to determine the adjoint modes. And the reason why I did not think about it, we are typically focusing on the experiments. And so almost all our techniques, most of the techniques which we are developing must have some application in the experiments, and adjoint does not belong to this class. Thanks.
I would propose to move the discussion to the hall with some coffee. So I will take again Professor Noack for this lecture. I'm very curious about this